Okay, welcome to the class, and you see this topic 5G demodulation reference signals. Okay, we discussed how they are used in the last class. Okay, now we'll see how they are defined in the standard. Okay, there's a lot of flexibility which the standard provides while defining them, and we'll see why such flexibility is there and how to use that. Okay, that's the key idea and the main motivation behind this class and the next class. Okay, so just to recapture, what are three different kind of reference signals which are defined in the standard? Sounding reference signal, okay, for uplink channel estimation. Okay, this is uplink focused, correct? And what is its downlink counterpart? That is CSIRS, okay, for downlink. Okay, then DMRS. Okay, before we talk about DMRS, we discuss the use of CSIRS for MCS calculation. Okay, please remember that this is not the only use. Okay, the use for multiple other tasks. I have not told that to you till now. Okay, so if I get an opportunity, we'll discuss other uses of CSIRS also. Okay, but don't get like tunneled by that effect that this is only used for MCS calculation. Okay, it has wide variety of uses. Okay, so this is CSIRS, we have seen that also, and finally what we saw was DMRS, okay, for channel estimation for demodulating data. And this DMRS, they are transmitted in both downlink and uplink. Okay, key difference between this and other two is they are transmitted before data transmission happens. This is transmitted along with data. So data can be PDSCH or PUSCH. Okay, even if it is PUSCH transmission, DMRS will be transmitted, because the use of DMRS is to give instantaneous channel information to the receiver. So the receiver can be user or the base station, doesn't matter. Okay, right? So this is used for both downlink and uplink, and similar use. Okay, the idea remains the same because the end objective is the same. Okay, right? So now we are going to focus how these DMRS are defined in the standard. Okay, that's what we'll look at all the gory details. Okay, of how they are defined, why they are defined like that. Okay, right? So let's get going with that. And so these are few general facts about DMRS. Okay, we know how DMRS are used, right? Okay, whether it's like single layer transmission or multiple layer transmission. We discussed their use for NL is equal to 1 and NL is equal to 2. But it doesn't matter, once you have learned it for NL is equal to 2, you can scale it up for any NL. The idea remains the same. Okay, right? Now, first key aspect which I did not tell you till now, and it was not even required for our previous discussion, that they are located early in the transmission. And what do we mean by that? Okay, that like even before the data comes, DMRS will come. Okay, I'll show you the pictures. Okay, how they come. Okay, and why? So they come early in the transmission and they help in achieving low latency. I'll show you how. We'll discuss this aspect. Okay, so they are coupled. They come early in the transmission. It helps in achieving low latency. Okay, right? So sometimes they are known as front-loaded reference signals. Okay, loaded in front of data. Okay, correct? And so that's how they are. One configuration I'm showing you. Okay, what is this type A? I'll come to it. But what is this? This is one PRB, right? Okay, one PRB over 14 symbols. Okay, so this is the frequency axis, and this is the symbol axis, time axis. Correct? 14 symbols. Look at this, 0 to 13. The index is running, right? Time index, and this is the RE index, the subcarrier index. Okay, right? So you see this. What is happening here? The DMRS is coming in the third symbol. Okay, correct? And let's see this. So why it is not coming in the first two symbols? Any guesses on that? Why? Because typically the first two symbols are used for PDCCH. Okay, right? And this aspect is mentioned later. So this is basically used for PDCCH, and they have their own reference signals. We discussed that. Core set, remember that? Okay, right? The way this core set was defined, it had its own reference signals, right? And UE uses those reference signals to decode its DCI, right? So this is independent. Okay, it is nothing to do with the design of this is separate. Okay, of course it has everything to do with what comes later, okay, but the design of this is completely independent from this. That's the aspect one has to keep in mind. Okay. Now, so what is this front loaded? You see this. So this is basically the data is coming. Okay, I'll explain all these terms. This term mapping type A, I'll explain everything in detail. But look at the point I'm trying to make here is that this is where the data is coming. Okay, right? And you see where DMRS is coming. Correct? Okay. So of course by now UE knows where its data is located because it has decoded its DCI, it has figured out its data is coming here. Correct? Okay. Now as soon as it starts receiving this data in the downlink, what will it do? It will basically use this DMRS to start estimating its channel. It doesn't wait for the rest of the transmission to happen, it doesn't wait for this reception. Okay. Correct? Right. So it gets this DMRS, starts estimating the channel. Right. So, and what is happening with this? You are basically cutting down on the processing delay. Correct? If this instead of this front loading, if you make it load it at the back, okay, you'll have to wait for the complete 14 symbols to come, and then only you can start estimating the channel. Why? Right? Okay, because you cannot do anything without estimating the channel. Right? Why make the receiver wait for this DMRS to come? So typically they come in the beginning of this PDSCH transmission. Front loaded, low latency, all these objectives are achieved, okay, because okay, this is not an objective, front loaded in the front, this low latency objective is achieved, right? Okay, correct. So it allows the receiver to obtain a channel estimate early, and what happens? It processes receive signal on the fly without buffering a complete slot prior to data processing, right? So let's look at this reduced memory requirement. It can start estimating the channel, then it can process the data of each symbol. It doesn't have to wait for this complete slot to arrive and then process its data. It cuts down on the memory requirement. For the people who are working on implementing these modules, you should ask them, okay, then how much of memory it saves, okay, right? So, and this is how you do your cheaper receiver design, okay, you have cut down on the memory, correct, you have cut down on the delay, okay, right? So all these are, this is basic common sense, nothing more than that, okay, there is no like fine engineering involved in that, okay, good, fine, okay, right, but these are the key aspects, okay. So you see the standards are designed like that, most of the time it is common sense, okay, and these things only work. Okay. But of course, it doesn't mean that then like you should not know about the fancy things, because you saw about MIMO transmission, you saw all this, how all these like control coding, interleaving, they are fine, nice modules. Okay, you should know communication theory to understand that. Okay, these ideas common sense. Okay. Now there are two different time domain DMRS structures are defined. Okay. And they are type A and type B. So you see this type A, I'll explain what this type A and type B are, okay. Each one of them has its own use. So you see this, we are getting into the details of how DMRS are defined, okay. We just know as of now how to use them, correct, okay. How they are defined, why they are defined, we are starting to see that, okay. And see, another thing is that if there is only one DMRS coming over here, okay, you estimate the channel and then you use it for the complete PRB. What is the basic assumption you are making here? That the channel doesn't change for all these symbols, correct? Okay, and so if channel changes, it will change. Okay, if UE is moving at the speed of 500 km per hour or any like high speed, okay, so it will change. Okay, even at like 50 km per hour, channel changes. Okay, so how DMRS allocation is done in that case, that's what all these type A and type B are. Okay, so basic idea will always be like it will be used for demodulating the data. Okay, how they are configured and what frequency they are going to come, that's what these type A and type B are. Okay, fine. So let's see that. Okay, so we are going to focus first on mapping type A. Okay, there are two types, type A and type B. Okay. We will look at type A mapping. Okay. And what am I saying here? The type A mapping is intended when PDSCH occupy most of a slot. Okay. You have like the data is such that the PDSCH occupies complete slot or like most of it. Okay. What could happen where this, okay, wherein there are other kind of transmission, just it will make sense when I briefly tell you about type B. Okay, that is used for URLC transmission. Okay, URLC transmission can come anywhere in a slot. Okay, and it will occupy a small part of the slot because some very like low latency data, but not high bandwidth data or not high amount of data. Okay, right. So that's where type B mapping is used. We'll see all that also, but I have to tell about type A, so I am telling you about type B also. Okay, so type A is normal transmission. Okay, wherein like high bandwidth transmission, but not emergency transmission. Okay, and it occupies most of the slot. Okay, so data in 5G can occupy lesser than a slot, that is there. Okay, but still it will occupy most of the slot. And depending on how many slot the PDSCH is occupying, you will have different configurations of type A. Okay, we will see that. So this is the figure I showed you on the last slide. Okay, so this is basically type A. You see this in this figure, data is basically occupied till the 11th symbol. Okay, correct. So most of it, 3 symbols are left. So they are used for something else. Maybe they are used for uplink. Okay, or some other user. Okay, fine. So so this is where type A mapping is applicable. Okay, and so you see this first DMRS is located in symbol 2 of the slot. Okay, I jumped the gun and told you why it is not located here, right? Okay, so we know that why it is not located here because it is PDCCH. Okay, now in this mapping type, okay, which is type A, DMRS location, this is called L bar. Okay, location L bar is mapped relative to the start of the slot boundary. Start of the slot boundary is this. Right? This is a boundary. Okay, right. So if I say that the DMRS is beginning at second symbol, so of course it is from the beginning. Okay, you understand what I am saying here, that this DMRS location is told. Okay, whenever I tell that DMRS is located at second symbol, it is basically from the beginning of the slot. Okay, it will change when the mapping type is B. Okay, right. So see this. Okay, so and what is this L, and then so L bar is the starting location. Okay, and LD, you see this, let's read this, is the duration between the first OFDM symbol of the slot and the last OFDM symbol of the scheduled PDSCH resources in the slot. This to this. This is LD. What is L bar? Okay, it tells the starting location relative to the beginning of the slot. Okay, and LD is basically the duration between the first OFDM symbol of the slot and the last OFDM symbol of the scheduled PDSCH resource in the slot. So LD is this, not this. That's how it is defined. Okay, it will change for type B. Okay? So that's why I'm crucially pointing it out to you. Fine. Okay. So let's see that. So DMRS is located in symbol 2 in the downlink because of the facts we know now. Okay. PDCCH, which is located at the beginning of slot, which has its own DMRS, right? Okay. So we have discussed that. So DMRS can be located in symbol 3 if PDCCH occupies 3 symbols. So PDCCH can occupy third symbol also, depending on how many users DCI you are sending in the PDCCH. Okay, right? So, and typically it occupies 2 to 3 symbols. Okay, so if PDCCH is occupying 3 symbols, it will come here. The DMRS will come here. Okay, in this picture, it is only occupying 2 symbols. That's what this bullet is telling. Okay, right? So these are. See, you will have to configure. Base station has to configure the DMRS. Okay, how is it going to configure? It's going to configure like that. Okay. And mapping type A, mapping where is it scheduled, okay. This is, you will see that all this information has to go in the DCI. It has to be told, correct? Okay, where this DMRS is scheduled, right? Whether in this symbol or this symbol, okay, you will see that a lot of flexibility will come, okay. So it has to be told, okay, right? So this is, you see this is over 1 symbol, correct? Okay. Now I'll show you another configuration in type A itself. Okay, so we are only focusing on type A as of now. The earlier DMRS was single symbol. okay. And what I am going to show you is double symbol, okay. So DMRS can span over 2 consecutive OFDM symbols also, okay, like this, okay, right. Earlier DMRS was single symbol, this is double symbol. It will be told, okay, you of course knows about all this, that this is how its DMRS is coming. And why is it spanning 2 symbols, okay, and the reason here is used for defining higher number of orthogonal DMRS ports, okay, right. You see this, if basically you need only, I mean, if it is a 2-port DMRS, you need at least 2 subcarriers. If it is 8-port DMRS, you will need at least 8 subcarriers, okay, right. So as the number of port increases, the number of resources required for defining DMRS is going to increase. So this accounts for that, the second symbol accounts for that, okay. So that you, instead of 12 resource element, you have 24 resource element to define a DMRS which will contain larger number of ports, okay, right. So, and that's, the idea is clear, that as the number of port increases, the number of resources required to define the port will increase, and this accounts for that, okay, right. Just give an example that from 2 to 4 you will need at least 4 resource elements, okay. Now, so what happens, okay, that although these front loaded reference signal reduce the latency, okay, that they have come in the beginning, okay, saw that whether it was single symbol or double symbol, they were coming in the beginning of the PDSCH transmission, right, okay, that, and we know the objective, reduce the latency, okay. They may not be sufficiently dense in that time domain in the case of rapid channel variations. What am I saying here? We'll decode everything, okay, right. The channel is varying fast, correct, okay. User is moving at a speed of very high speed, okay, or moderate speed or a low speed, okay. Depending on that, okay, the channel will change within a slot, okay, right. So, and how fast does it change, okay, that base station, let's say, has the complete information. How does it figure out? That's left for future discussion, but it has this information that UE is moving at a slow speed or moderate speed or a high speed, okay. Now depending on that, it can send 3 additional DMRS time domain occasion in a slot, okay. That's how it is written in the standard, okay. What does that mean? Let me show you this, okay, correct. So what was this? This was only 1 DMRS, okay, coming in the second symbol. Now let's say UE is moving at a moderate speed, okay. Base station knows that, okay. What will it do? By the time this this part of the symbol comes, okay, UE channel has changed, okay, right. So it will send 1 additional DMRS towards the end of the slot, okay, correct. So see this, that's the configuration, that's what we are talking about, okay, that how DMRS needs to be configured. And this also standard only tells you that these DMRS are defined, okay. How to configure them, it's entire the designer's decision, it's entirely the scheduler's decision, okay, that's where scheduler will again come into picture, okay, that it needs this information, that how fast the user is moving, okay. So it will get that information, let's assume that, okay. Then based on that, it knows that it's moving at a moderate speed, okay, right, typically 20 kilometer, 30, 40 kilometers, okay, right. So now this is 1 additional location, this is called, see, what you should read this, up to 3 additional DMRS time domain occasions in a slot are allowed, okay. So this is 1 additional, this is basic, this will always be transmitted, okay, right. So this is 1 additional DMRS occasion. What happens here? Speed increases, 2 additional occasions, correct, okay, and if highest speed, that's what it is supported, okay, in release 15, okay. I am not sure about other releases whether the DMRS density is further increased, okay, because if you still design the standard for a higher speed, then you'll have to further increase the DMRS occasions, but till release 15 there are 3 additional DMRS occasions which are defined, okay. right? Now you see this, if you do a bad system design, okay, if you do if the scheduler does not take care of the fact that like U is moving or U is stationary or is highly mobile, okay, always, let's say it always transmits 3 additional locations, then you are using a lot of bandwidth to transmit unnecessary information. Your user's data rate is reducing, right? Correct? Okay, because all this will be accounted during rate matching. Correct? Right? So, because rate matching will tell you how many resource elements are there in per PRP. That's, you remember that formula. Correct? In that formula, all these were accounted for additional overhead. So this is that additional overhead. At that stage, I could not tell you. Okay? So this additional overhead is going to reduce the number of resource elements. Correct? Okay? Now, this is the other extreme. U is moving at a very high speed and you don't allocate additional DMRS. So channel has changed. U is using the H channel to decode its data. Again, it will create errors. Right? Okay? So it's going to like lead to a knack. So that's a system design. Okay? Correct? And so typically what people do is initially design the system which doesn't support mobility, so that, okay, you show that system works. Then you say, okay, I want to, like, my system will support mobility, so you'll have to configure all that. Okay, so okay, it supports pedestrian mobility or like low vehicular mobility. You'll configure, then you'll have to decide, correct, whether it's this or this. What people typically do is it's difficult to get this information, the speed of the user. So you configure this. Okay, live with that. You always send this. Okay, it's a bulletproof way. Okay, that it will support at least pedestrian mobility or low vehicular mobility. So there will be some degradation, of course, in the throughput because you are always transmitting this. Correct, but you don't need that. The scheduler doesn't need that speed information. It's a dumb way of doing it, but then you progressively evolve. That you get that information, scheduler gets that information somehow, and then either this or that. Okay, then there are other options. Okay, you see the flexibility, you see the importance of scheduler design. Okay. So channel estimator in the receiver can use this additional DMRS for better channel estimation. Correct? Okay, right? For example, to interpolate between the DMRS within a slot. What will happen? Okay, so UE will estimate the channel here, you will estimate the channel here. What will it do for this intermediate, this one, symbols? It will interpolate the channel. Correct? Okay. Now, what kind of interpolator you design again? The UE designs. It's again the is the function of the processing power UE has. Okay, if it is an like 5,000 rupees phone, it will simply copy these estimates here. It will not interpolate. Okay, copy these three estimates here. This estimate for 3 symbols, copy estimate for 3 symbols, and somewhere do averaging in between. Okay, right? So these are the kind of games which are played while designing a system. Okay, right? So so this is where you see these additional occurrences are being allowed. Okay, right? So 1 additional, 2 and 3 additional occurrences are being allowed. Okay, correct. Now what happens? There are certain cases wherein this additional occurrences are not allowed. Okay, we'll see that. Okay, that's what I'm going to show. Discuss the case when no additional single symbol DMRS can be transmitted. Okay, there are 2 different kind of transmission. Right? I showed you here additional occurrence only for single symbol. Okay, even the 2 symbol can be there can be additional occurrence for 2 symbol transmission also. I'm not showing you here, but that's also possible. Okay, right? So is this clear? What are we showing here? That in certain scenarios these additional occurrences are allowed. Okay, in certain scenarios the additional occurrences are not allowed. Okay, I'm looking at the single symbol DMRS where these additional occurrences are not allowed. Okay, so what's happening? Okay, if the PDSCH duration is between 3 to 7 symbols, okay, right, like this, then because you see that data is not being transmitted in the rest of the symbols. Okay, there is no need to configure additional DMRS occurrence. Okay, right? So standard prohibits the transmission of additional DMRS occurrence because data is not scheduled in the most of the slot or in this part of the slot. So what is it saying? If the PDSEH duration is between 3 to 7 symbols, okay, right? So this is ID is equal to 3 and this is ID is equal to 7, okay. This LD is between 3 to 7, okay. So if the PDSEH duration LD is between 3 to 7 symbols, okay, right? So DMRS location L is always L0 is equal to 2. This is L0 is the location of the first DMRS symbol, okay, right? So what are we saying here? What did this slide tell you? Okay, in the previous slide I told you that the additional DMRS occurrences are possible, fine, okay. You see that, okay, right? Now in the next slide what am I telling you? In which case these additional occurrences are not allowed. And what am I showing you? If the data is coming till here, correct? Data is coming till here, you know that channel will not age, okay, most likely, because even if you move at a high speed, channel ages, you see its effect coming only after 7th symbol or something, okay. You see that, where are these additional occurrences coming? Okay, here not 7th symbol, okay, here again after, right, okay. So this is the second occurrence. You can say that here it is coming, okay, right. But before that you have already defined these occurrences, which essentially means that data is spanning the whole slot, correct, okay. Because how did you define? First you defined this, which the basic assumption is that data is spanning the whole slot. If data is not spanning the whole slot, you don't care, right? Then this is defined. This is additional occurrence, okay, correct, okay. So if data is coming till here, then what standard says is, forget, you don't assign any additional symbol, DMRS symbol, correct, okay, right. So and in this case, so this DMRS location L bar is the DMRS location, L0 is the standard uses for the first DMRS location. So L0 is what? L0 is 2. This is L0, right? Location of the first DMRS symbol, which is 2, second symbol. Okay, and what are we saying? LD, okay, which is the duration, is between 3 to 7 symbols. No additional DMRS is allowed. Okay, right? So we'll continue discussing this in the next class. Okay, what are the additional flexibilities which are provided for DMRS? Okay, I'll stop here. We'll take it up in the next class. Thank you.